week 3 of network structures and cloud computing. Today we're going to talk about workloads and software infrastructure. We're going to start off with some terminology. Platform level software is the common software, firmwares, and operating system and libraries mainly to abstract the platform from the user. So essentially it's everything that goes from the cluster level infrastructure to the prompt that you get from your VM to basically execute your workload. And then we have the cluster level infrastructure, which is the collection of the distributed system software that basically aggregate all the platform level software into a group of resources, and then it manages it. It provides a service at the cluster level, also known as the data center OS. Essentially, it's a system like Hadoop or Kubernetes. If you had a chance to read a few things about those systems, so we have a bunch of Linux instances that are running on some hardware, and then you have another layer that actually manage all these things. Okay. On top of the platform level software, we have the application level software, which is what we essentially use. This is the part that provides value to the user. And the canonical examples is Google Maps, Waze, Facebook, and so. Another important term is eventual consistency. So let's assume that we have an architecture that requires several replicas, several processes that are running in different locations. When we talked about in the other, I think in the last session that we had, we talked about availability and resiliency to error. What we don't want to have as a user, as a Facebook user or as a Google user, to get an error page that says, sorry, we are not available. So what we need to do is that when we build a cloud service, we need to make sure that even if something will fail, and things will fail because hardware fails, and software moreover also fails, so we need to have some sort of a mechanism that will take care of that. And eventual consistency is the case where things fails, although that the application did take care of replicating and notifying other instances to take care of data that was populated in the system. Eventual consistency is the case where things propagated across all the participating data centers and replicas, but it didn't completely diffused on all the services. So eventual consistency is saying that eventually all the nodes that participates in this clustering will be notified with the new with the updated information. Now, this is sometimes problematic to some applications, and this is why I'm emphasizing this term specifically. For example, banking. There is no such eventual consistency, because if you want to know whether you have $1 million or $0, it has to be consistent across the board, because otherwise one can make a transaction of selling something for $1 million and then do another transaction on another node that he predict that the transaction was not propagated before. So this is an example of why eventual consistency is not a good candidate for a solution for banking and transaction-based scenarios. However, for search and other advertisement scenarios, that can be a good technique or technology to use. So basically, this is what I want us to start thinking about when we are talking about all kinds of mechanism and principles, we should always connect this thing back to the scenario of what the user tried to do. It's we're going to talk a lot about power systems, about networking, and very fundamental things in distributed system, but we always need to remember how does it related to the user scenario. Yeah, so cloud versus desktop, and this is just an oversimplification of a comparison between cloud and desktop. So cloud service exhibit large amount of parallelism, right? And the parallelism can come from humans, like Xbox state management in multiplayer game, Google search, many people are searching specific things, and it can come from the internet, such as Waze, for example. Real-time geo-positioning, and then it might come from both, like the stock market transactions. Okay, so people are buying and selling, and the systems are communicating with each other. So this is a cloud service. It's the core difference is that it exhibits large amount of parallelism. And then another aspect is continuous deployment. I think we talked about it before, and we're going to definitely discuss it more during this course. Continuous deployment is probably one of the important aspects when the operational aspects of running cloud service. Internet services are isolated from the service implementation, right? So it's not, the service itself is completely decoupled from the service implementation. So there is no, and internet services usually comprise of many microservices, right? So every microservice has its own role, and it deployed in a different way through a different cadence, right? So and this approach really allows those service providers to control the destiny of their service. So for example, if we have Google, if we take Google as an example, Google provides many services, Hangout, as we use in this course, Gmail, and then these services uses other basic services, independent services, such as the address book of all the user that are, or all the specific users that both services are using. So for example, when Hangouts wants to look, when I'm trying to look up for other friends that knows me or that I wanted to contact, I am accessing some kind of a microservice, which is some sort of an address book that is fetching the information for me, right? Although that I used the Hangout interface, I called to a specific microservice that deal with this thing, that holds all the addresses that are known to Google. So in this ways, you can build an architecture that every component can serve each other and build some sort of an ecosystem that fulfills scenarios for the user, as the example that I mentioned right now. An internet service usually comprises of many microservices, as I said, deployed in different cadence. Also, each microservice includes several application levels. Structure, such as front-end and back-end, and stateless and stateful tenants. Now, how all this is related to the continuous deployment? It is related by the ability to provide each service its own continuous integration and continuous deployment fashion. So if you as a service have your own new bits that you enrich in terms of features, you can deploy it ultimately all the time, regardless to the time of the day, or moreover, regardless the dependencies that other services that have on your service. And I guess that the goal in continuous deployment is allowing service agility. I can do things while you do things, and we all collaborate together. Another important aspect it is platform homogeneity. Cloud services is more homogeneous environment than desktop. Data centers deploy smaller amount of hardware and software components, right? And the more components, the more failure, right? This is an important aspect in these things, and this is why I said when we discussed about eventual consistency, the hardware and software fails all the time, and the more components we add, the more the greater the chance to have a failure. Some desktop will require high screen rendering capabilities, additional GPU, and then the data center will have a simple motherboard with a CPU and RAM. So every hardware requires more power, cooling, etc. So I guess that the point here is that desktop supposed to serve for specific scenarios where you need to do all kinds of sophisticated things for the users. When you look at the hardware that the cloud services are using, these are very, very, very simple things. They supposed to have CPU and RAM and some motherboard that can achieve density of both CPU and RAM, and essentially serve as much capacity as possible, and basically provides both networking and compute capabilities. Every hardware requires more power, cooling, and etc. And this is as opposed to our desktop. Fault tolerancy. Fault tolerancy is a really interesting aspect, and I call it out with a question of what is worse, desktop cache or server cache. So if you are running on your desktop and you are working on your project and your desktop caches, this is a very bad thing, right? And if you run on the server, when you run your workloads on the server and the server happens to run many other workloads of other service such as you and its caches, it's also very bad. It's bad for other users. So I guess that the question here is to trigger some kind of a discussion of it's not about what is worse, it's about distinguishing between the impact of both cases. Okay, cloud services runs on clusters with thousands of machines, and faults are part of the cloud service daily life. And this is a very, very, very important aspect in cloud computing. As we said, cloud, regardless to the software that we run that can fail, software are running on the hardware, and all these components are prone to fail. And this is why we need to remember it when we build the architecture of our cloud service. Performance and availability techniques. One of the things that comes to place after we understood that both hardware and software will fail is that how we make sure that the application that we run, as we said, Facebook and Google and Xbox and all the good application, how we make sure that they are responding within the acceptable SLA, service level agreement, or the user expectation, and that they are available. So going back to the fact that we just discussed about you are opening the app, you don't want to get 404 or 500 like errors, because if you're gonna get errors, guess what? You will not try it again, because who wants to be who wants to use a service that is up and down, because it's not reliable and it's not fun. So this is why there is a lot of thoughts that are around availability, and also we don't want to have a situation when we are pressing on, we're clicking on some post that we saw on Facebook and it's taking ages to load. So we are simply going to quit and not use it anymore. So this is why performance and availability are important. Now, replication is it's a technique that helps to improve both performance and availability, because you can imagine a case where you have two instances that are serving the same workload, and by the way, we are going to implement such workloads in class. And when we have these two, if one fails, there is another one that can serve the users, and vice versa. So, and if both of them are running, then you can have more capacity, right? And you can actually split the work among two. So I hope that you understand that how high availability and how replication improves both performance and availability. Sharding. Sharding is a synonym for partitioning. It's basically splitting data set into smaller fragments, okay, shards, and distributing it across large number of machines. So for example, if you have a large database, okay, and sharding can confuse sometimes, because there are several types of sharding. Because one type of sharding is that I have a large set of database and I want to shard it and spread it across several areas, okay? And every time that somebody is asking for a specific data, some application level asking for specific data, I have a mapping a service that knows to tell me where to fetch this data. So this is another way to relieve the pressure on one particular instance that holds all the data. Another thing about sharding, another type of sharding technique is replication. As we discussed, you take every bit that was written into one place and you spread it across other replication instances. So when the instance is overwhelmed, a particular instance is overwhelmed, or went down from some reason because of a hardware failure or a software failure, there is a failover that other application can serve this data. And load balancing is actually the technique that orchestrates across all the replications or shard or partitions that we created. So basically we have a one component load balancer that accepts all the traffic, all the ingress traffic, and ingress stands for the incoming traffic, and then basically distributed based on some criteria, and we can talk about it later, and provide and move and divert the traffic to the processing component that essentially return the results to the user and provide basically the user experience. Health checking and watchdogs, those are the things that are happening in parallel, concurrently to all the good things that we said. So for example, when we discussed the scenario where we have a load balancer, when a user click on our service, it is getting diverted into some specific node, and this specific node might need some data that is getting replicated across several partitions or n replications. So you fetch the data and you serve it to the customer, now to the end user. Now health checking is something that happens constantly as the system is working. So when we know how to check the health of the service on every component that serve the users, we know how to act proactively for unexpected cases, such as the failure that we mentioned, hardware failure and software failures. So failures are manifested as slow or unresponsiveness behavior from the service. Health checks can be terminated. Health checks can be terminated on different application layers. So basically, this is a technique that we check constantly. Are you okay? Are you okay? Are you okay? And if I don't get any response, I can assume that you are not okay. Or we can check we can take essentially different approach and different techniques. And then there is the integrity checks and eventual consistency, as we discussed before. Okay. So now let's talk about cluster level infrastructure software. As we said, its core goal is to manage the pool of resources that we have from the hardware and schedule all kinds of tasks. And the task can be launch a VM on node A, and resource management is basically understanding how much CPU do I have, and if I get a request such as launch a VM, I should first of all understand, do I have enough resources to provide this basic task management services. Scheduling for synchronous and asynchronous tasks, we talked about it. Hardware abstraction, so this is another important thing. Cluster level infrastructure provides hardware abstractions and basic services. For example, allocation and deallocation of services, bootstrap power off and powered off hardware, deployment and maintenance. We talked about continuous integration and continuous deployment. We wanted to have services from the cluster, from the infrastructure, that we can, as a tenant, can take a new software and push it and install it into our VMs. So this is like, think about it as the installation program on your desktop. Okay, but again, something that this is a service that runs in scale. Application level software, it's basically their workload, as we said. There are two different workloads. There are other classification. There is online and offline. When we say offline, I mean that when I'm saying, so let's start with the online. The online is some web search that one do, some looking at Facebook or logging into your bank. Other low latency is live streaming, for example. You want to watch TV or Netflix, so then you have a low latency application that requires to return to the user immediately. The offline workload is something that you have a bunch of data and you need to basically process it, and you don't have to wait. There is no user that is actually waiting with some terminal or staring at a screen and waiting for your response. And this is high latency, as you can understand. And processing of larger amount of relatively independent data sets, billions of web access logs, Apache access log, this is what we are going to do as part of our practices. And monitoring infrastructure, the service level, the monitoring infrastructure supposed to provide 3 layers. Okay, the first layer is the service level dashboard. It's how the application level software does, like what the user feels, and how you implement such a dashboard. You basically look at several places, several endpoints that signify the user experience, and you simply send some sort of a synthetic workload and determine whether the workload is processed as expected. Now there is once that you discover some problem, how you debug the problem, and how you check that the performance of the system is ready to consumption by the other user. And we're going to learn how, and we're going to learn and use such tools, debugging tools. We're going to use mainly JMeter, which is one of the open source that is offered by Apache, the Apache project. Yeah. So now I'm going to talk about the practice that we are going to do for this session.